Welcome back. So we've entered a new part of the course, which is, as I said, the effectively the final stretch. And it's really tied to the previous part, which was about life as defiance. But now what we're doing is we're trying to introduce active matter and field theories. And so the point of this vignette is that I want to try to give an indication of how on earth is it possible that the thoughts of people like Euler, who was trying to figure out how to treat fluid motion, and then people like Faraday and Maxwell as they came up with ideas of the electromagnetic field, how on earth is that relevant to our thinking about morphogenesis in Drosophila or in C. elegans? Why should I be talking about field theory? So I want to try and give that background in this particular vignette. I'm going to start with a bit of a historical aspect by introducing one of the greatest, if not, I don't know, it's hard to, it's kind of like deciding who's the greatest sports athlete of a given kind in all time. There's some element of subjectivity about the criteria that one uses, but one could for sure make an argument that Michael Faraday could be considered one of the greatest experimentalists that physics has ever known. And if you're not aware of his personal story, it's so incredibly inspiring. And frankly, if back when we get around to traveling again, if you happen to go to London, you can go to the bookstore where Faraday was a bookbinder's apprentice. So I'm going to give you the rough sketch. You can go read about Faraday's biography. There's a number of really excellent ones that tell the story of this remarkable scientist. And so the essence of it is that at a very young age, 12, 13 years old, Faraday was basically, I don't really understand, what it meant contractually, but he was made the apprentice to a bookbinder, but in some sort of a formal way between the ages of like 13 and 18, something like this. And what that meant is that he worked at a bookbinder, and he was just I want to register that again. It's the same words apply to Alfred Russel Wallace. We're talking about at a very young age, basically discontinuing school and not being put off by that, by having such a thirst for knowledge, a thirst to understand things, that they found a way to make it happen. And I think we can all draw inspiration from that. It's very easy to get into the rut of feeling like you need to go through some formal mechanism. But the beauty of the fact that we have what Clifton Fadiman referred to as the great conversation, the fact that people can write down the written language allows us to have conversations over 1,000-year timescales. I have a friend who has been having a conversation with Herodotus, which I find that so beautiful in many different ways. So at any rate, Faraday was quite the reader, and he ended up writing a letter to Humphrey Davy, who was at the Royal Institution, saying, I basically put together a series of notes about your lectures, and I'm wondering, I'm gonna exaggerate the words, or I'm gonna get it a little bit wrong, but effectively, can I come and sweep your floors? And Humphrey Davy engaged him. And before long, Humphrey Davy saw that this was a remarkable young talent. And he took Faraday with his wife, and they went to Europe. That was back at a time, we're talking like the 1820s, when going to Europe was a multi-month excursion, and he went to Italy and he met people like Arago and other famous scientists along the way. And when he got back to the Royal Institution, he continued to help Humphrey Davy with his experiments, but before long, he was an independent researcher. And again, this is another thing that's well worth your time in London, is to go to the Royal Institution. You can actually see the apparatus that Faraday used in order to, for example, discover electromagnetic induction. Yes, I'm giving you a course on biology, but there's a unity to nature. There's a unity to science. And the whole point of this course is the belief that the study of the living part of this amazing universe we live in is not somehow the exclusive domain of the subject we call biology. It's every man and woman for themselves in terms of what they're curious about and what it means to them to understand things. And so in this case, I'm arguing that we are intimately tied to the musings and the experiments of Michael Faraday, who wrote a number of papers that were bound together. This is one of my treasures from when I was a kid. Faraday's experimental research in electricity, and one of the most remarkable figures in that book is shown on the right, and I certainly remember this again from when I was a kid because I was so intrigued by something that's sort of high school level exercise now, where you take iron filings and you have a piece of paper on top of a magnet and you sprinkle the iron filings, and you'll basically see those iron filings align in a way that give you an impression of the field lines. And that's overly trivial. It doesn't, as with many things, it does not really convey an impression of how profound this was. And so, Faraday basically articulated an idea of a space that is penetrated by electric and magnetic field lines everywhere. And the reason that that's important, as I will say shortly, is that it took the dialogue off of the material particles and started to endow the space between them with its own significance. So, along came James Clerk Maxwell, who wrote 3 or 4 super important papers in the 1860s. And then he codified all of that in his book, which is called A Treatise on Electricity and Magnetism. And in it, I want you to see the right-hand column. This is from the preface. As I proceeded with the study of Faraday, already that's great. So here he is, reading Faraday, who was something like 30 years his senior. And they had a great correspondence, and they respected each other immensely. But Faraday, as I told you, was a bookbinder's apprentice. He, like Charles Darwin, had no mathematics. And so, at any rate, Maxwell made this remark. He said, I actually made a point of studying Faraday, not the other mathematicians. So as I proceeded with the study of Faraday, I perceived that his method of conceiving the phenomena was also a mathematical one, though not exhibited in the conventional form of mathematical symbols. And let me prove that to you right now. So if we go back to this figure, you can look at these pictures, but anybody that's had first exposure to sort of freshman physics, and I don't say that in like a pompous way, I say it actually in a way almost critically, because I'm so frustrated by what the freshman experience is. This is no comment on my employer or Caltech or anything like that. I'm beyond grateful to be part of the Caltech community, and it's a merit I did not deserve, so it's my good luck. I'm not talking about that. I'm talking about it as a fiercely independent and relatively angry guy who feels that education largely is soul-crushing. And so I feel like, freshman versions of any subject are taught as though the people that are listening are going to become majors. And, the place that I notice this perhaps most obviously is when I go to doctors. I have many long-term relationships with doctors in California and in Rhode Island. And, I like chatting with people and hearing their impressions. And almost always, doctors will tell you, oh, physics was my worst course and my hardest course and most incoherent and most useless. And, how pathetic is that? How wrong is that to have physics by a medical doctor be perceived as sort of, like a hurdle? So at any rate, I'm saying in freshman physics, somebody told you about electric fields. And one of the beautiful ideas, but very hard to appreciate, is something that's known as Gauss's law, which tells you to draw a surface around a charge or around a magnet, for example, and then you integrate the lines that are piercing through that surface. And essentially what you have, let's take the sphere, is you have the electric field, which is normal to the sphere, times 4 pi r squared, which is the surface area of that sphere, is equal to the charge that's enclosed by the sphere divided by a parameter epsilon naught if you work in a certain kind of units. Now, this is what Faraday was talking about, and this is what Maxwell meant when he said Faraday was mathematical, because Faraday knew that the density of the lines that you see in this figure, was related to what we now refer to as the electric and the magnetic flux. Anyway, okay, so I also found that these methods were capable of being expressed in the ordinary mathematical forms and thus compared with those of the professed mathematicians. For instance, Faraday in his mind's eye saw lines of force traversing all space where the mathematicians saw centers of force attracting at a distance. Faraday saw a medium where they saw nothing but distance. Faraday sought the seat of the phenomena in real actions going on in the medium, they were satisfied that they had found it in a power of action at a distance, impressed on the electric fluids. When I had translated what I considered to be Faraday's ideas into a mathematical form, I found that in general the results of the two methods coincided so that the same phenomena were accounted for and the same laws of action deduced by both methods, etc. So really, Maxwell is saying that Faraday's conception of the field was an intrinsically mathematical one. And, I already talked about this earlier in the term, so I'm not going to belabor it now because I likely will bring it up a third time. Obviously, I'm deeply passionate about it, and I believe you should be too. It's a subjective opinion, but of all the scientific truths figured out in the history of humanity, this few pages of this book is shocking. And what it is, as I said before, is that Maxwell worked out a wave equation for electric and magnetic fields. That's shown at the bottom. The details don't matter. And wave equations feature a velocity squared. So on the right-hand side, that's a 1 over a velocity squared. And his velocity featured two units, which were things that were known from magnetism and from electricity, but had nothing to do per se with light. And yet, as he tells us here, hey, I put in the numbers and I found out that it's more or less the speed of light. Wow, So when Einstein was at college, so I'm teaching at a college, I'm teaching at Caltech. There's lots of undergrads in this course, and I think about this all the time. Einstein was frustrated because here he is in 1890 something or other, and that's 30 years post Maxwell articulating the equations that bear his name, and in the lectures by Weber that Einstein took, it was on classical physics. They didn't talk about Maxwell's equations, and what Einstein had to say was the most fascinating subject at the time that I was a student was Maxwell's theory, and so one of his classmates said of Einstein, his meaning Weber's lectures on classical physics were lively, but we waited in vain for a presentation of Maxwell's theory. We knew that it confirmed the identity of transmission of electricity and light, and that Hertz's investigations on electric waves had confirmed the theory. Einstein, above all, was disappointed. And what I'm also showing you there in the middle of the page is a page out of the Feynman Lectures of Physics, just to point out, that in some sense, when Feynman tried to embody, the essences of classical physics, well, there's really two field theories there. There's the Maxwell theory, and then at the bottom, there's a gravitational field theory. We could think of a gravitational potential permeating space or gravitational forces, and et cetera. And so, I'm just trying to give you a sense of the significance of field theory, and I think, I really don't like citing authorities. I find that to be annoying, and science is not law. We're not trying to cite authority figures or precedent necessarily. But I do think it is interesting to see that one such as Albert Einstein, in the Evolution of Physics book, which is really worth reading, says, a new concept appears in physics, the most important invention since Newton's time. I didn't say that. Einstein said that. The most important invention since Newton's time, the field. It needed great scientific imagination to realize that it is not the charges nor the particles, but the field in the space between the charges and the particles, which is essential for the description of physical phenomena. And then Feynman. From a long view of the history of mankind, seen from, say, 10,000 years from now, it's very optimistic on his part, there can be little doubt that the most significant event of the 19th century will be judged as Maxwell's discovery of the laws of electrodynamics. The American Civil War will pale into provincial insignificance in comparison with this important scientific event of the same decade. I note, the year 1859, so 1864-ish is when Maxwell's equations came out. 1859 is when On the Origin of Species came out, and shortly before that is when Wallace and Darwin both acknowledged the theory of evolution. And, an argument could be made that, an equally or roughly equally important discovery of the 19th century was evolution, but it doesn't matter. I'm not trying to make that point, and I'm not trying to quibble over which was most important. I'm simply trying to say that this idea of field theory is so overarching in its importance. So we've already been exposed to field theory. We've used field theory. I just didn't make a big deal about it. When we wrote down the diffusion equation shown on the upper right, and we obtained diffusion 3 different ways. We used the coin flips, we used the continuum theory protocol, we used the chemical master equation, and it wasn't so hard. And what I mean by that, let's just trace our steps and remind ourselves of what we did. We said, well, we're going to replace the graininess of matter with a field variable called the concentration. And I think most of my listeners are used to the idea of concentration as a field variable. That means that there's a scalar quantity defined at every point in space that tells you how many particles, how many molecules there are. Then we imposed conservation of mass. We said, let's divide our whole body up into a bunch of small cubes, which get the fancy name of a material volume element. And then let's figure out the rate of change of the number of particles in each such material volume element in a unit time delta t. And what we found is that, there's stuff that comes in, there's stuff that goes out, and that accounting, it's nothing more than accounting, gives us an equation which is the continuity equation, which formally may be written as dc by dt is minus the divergence of the flux. That's fancy, but the concept you could explain to anybody. What goes in must come out, that kind of stuff. Then we made the more subtle point, which was we posited a material response, which was Fick's law. It tells us how flux and concentration are related through this very simple and, again, super far-reaching idea of flux being linearly related to degree of disequilibrium. Putting those two things together gave us the diffusion equation. So that's great. Once we have the diffusion equation, we can use it to solve all sorts of problems. What we're going to do now is we're going to do other examples of the continuum theory protocol. We will talk about the velocity field, for example, and that will lead to the F equals ma will lead us to the continuum equations of fluid dynamics shown at the bottom right here, the Navier-Stokes equations, which tell us how the velocity field varies in space and time. And you would know that if you go swimming in a river and there's some sort of a narrowing of the river, you speed up, you get rapids. You would certainly know it if you go out in the ocean on a paddleboard or whatever, and it's a day with some swell. You'll see that there is a velocity field. As I've mentioned, I've been riding my bike quite often across the Golden Gate Bridge. I have a game where I start out on Ocean Beach. I see a ship out at sea, and I race it to get to the Golden Gate Bridge. And often I get there just before it arrives. And I'm telling you this because it's super interesting to sit there and watch, to just observe and say, I wonder. So the other day I was there and a giant ship was coming in from China. And if you know the Golden Gate Bridge, you're looking out towards the ocean, and to your north is the Marin Headlands, and to your south is Baker Beach and the Cliff House and Ocean Beach and all that. There's a narrow gap, and as the ship came in, then it's trying to aim to get to the middle of the bridge. What I note over and over again is that the currents are so strong that just like an airplane sometimes has to fly a bit of it at an angle because of the crosswind, the currents are so strong that the ship is actually pointing, you can tell and watch as it's drifting towards the Marin Headlands. It's actually got to be pushing to avoid those currents. Why do I bring that up here? Because that kind of natural phenomenon is described by a field theory, which is the Navier-Stokes equations. So, we're going to be using these field equations again and again. I'm going to be interested in the context of active matter, for example, the spindle that I show you at the top. But we will pass through elasticity. We will pass through Newtonian fluids. We will pass through viscoelastic materials. For all three of those examples, I have amazing case studies that I want to tell you about. So for elasticity, we're going to talk about the beautiful work of Mahadevan and Cliff Tabin and Amy Shire and others, where what they did is they examined the question of gut folding. And I think you'll love that. And then when we talk about Newtonian fluids, I will talk about the work from Ray Goldstein, but that goes back many, many years on these long algal cells known as Cara. And in the context of viscoelasticity, I'm going to tell you about junctions in tissues. And this is work that I learned about from Thomas Lequi. So all of these, we will write down continuum descriptions, field theory descriptions, and we'll solve the field theory in some form or another. It might be an order of magnitude version of solving it. It might be an explicit solution, for example, in the case of Cara, which means we'll have to unearth the sort of heavy machinery of solving partial differential equations using separation of variables and things like that. So, I even want to note that our earlier discussion of positional information and Turing instabilities was itself cast in the language of field theories. So, we had a continuum protocol, a field theory protocol for Turing instabilities, which I show you here. And, that's been used even to think about things like the distribution of hair follicles and stuff like that. So we're going to consider a bunch of different types of field theories. So at the top, I show you the ones we've already done, which are scalar fields. So, you could think about the scalar field called temperature or pressure or concentration. Or if I'm thinking about a membrane, I can think about its height. We will think a lot about vector fields in the context of fluids, and there the central example will be the velocity field. That means that every point in space, there's a vector pointing off in some direction, and that's what we mean by a vector field. And then at the bottom, the more subtle example is the tensor fields, and there too, I will definitely be using tensor fields, and we'll talk about stress and strain. And the mathematical manipulations will become a little bit more complicated, but I hope that what you will keep in your mind is that over and over again, really what we're doing is accounting. That's really fundamentally what we're doing, is keeping track of the number of things or the amount of force or the flow of things in and out of little cubes. That's going to be our main idea. So I wanted to talk about the correspondence between molecular pictures and continuum pictures. It's, when it's working at its best, you actually can map back and forth between the two of them. And so I will, at least for elasticity, show you how you could start with springs and get from springs to stress and strain at the level of field theory, described by the Young modulus, just for example. And already back in the 1700s, Daniel Bernoulli was able to show how the collisions of molecules with a wall would give you what we now know of as at least pieces of the ideal gas law. Just because of collisions of molecules. So, that kind of thing is very interesting. And then we will expand our palette beyond sort of the obvious examples. When we try to confront active matter, we will think about things like orientation fields. That'll be a fun addition to the repertoire that we will have developed for thinking about elastic and hydrodynamic problems. So we'll sort of generalize. I think those are the main things I wanted to say. We will for sure look at the cell cortex. This is stuff done, for example, by Stefan Grill. It'll be a lot of fun to talk about flows in the C. elegans embryo and what role they have in setting up the anterior posterior body axis, and also think about asters. So that's what I have to say about the background on what is field theory.